this lab, we're going to investigate the law of conservation of energy. We're going to do it using a metal ball that's launched from a spring launcher. So the spring has some stiffness to it. We use the symbol K to represent the spring constant, measured in newtons per meter. Now the spring is relaxed when it's at the end of the barrel. So this represents the spring in its compressed state. So maybe we'll just describe this as location A for the metal marble. And then the spring decompresses, reaches its natural uncompressed length, but now the ball's up a little higher from where it started, and it's moving with some velocity. So there's a different combination of forms of energy available for the ball when it's at point B. And then it continues to rise to some ultimate height. At this point, it doesn't have any velocity. It's reached its maximum height. Of course, the spring no longer has energy stored in it, and we'll refer to that as point C. And what we're going to try to investigate is, does the mechanical energy at point A match the amount of mechanical energy at point B, even though the energy is in different forms? And is there the same amount of mechanical energy at point C as there is at point B or at point A? So the measurements we need to take are how far is the spring compressed when it's at position A. So we'll just call that D1. We also need to measure how much higher beyond point B does the ball rise. We'll call that D2. Of course, if we add those two distances together, that might be some meaningful value, so we'll call that H. And recognize that's just equal to D1 plus D2. We'll use a scale and we'll measure the mass of the ball. So that's some of the data that we're going to collect: the mass, the spring constant, the heights, and then there's one more measurement we need to take, and that's how fast is the ball traveling when it's at point B. So we're going to figure that out by making it pass through a photo gate. And what will happen is the very top part of the ball will register the photo gate, and that'll begin the timing process. Then the bottom of the ball passes out of the optical beam, and that stops the stopwatch. And so we're really just measuring how much time does it take for the diameter of the ball to pass through the photo beam. So we're going to say V is equal to capital D over T, where capital D is diameter. So you can see at point A, the energy that's available is stored in the spring. At point A, we have elastic potential energy. Now, whether or not there's any kinetic energy is clear. No, the ball's at rest at this point, so there's no kinetic energy. What about gravitational potential energy? Well, if we set a reference point, it's at the very top of the barrel is where height is equal to 0, then the ball would have some negative gravitational potential energy at point A. So we're going to change our reference system so we don't have to deal with any negative values. And we'll say our reference position for height is when the ball's at its lowest point compressed against the spring. Okay, so then what form or forms of energy does the ball have at point B? Well, the ball's now up above that reference height, so at point B, it has some gravitational potential energy, and it's in motion, so it has some kinetic energy. So what we want to do is use the formulas we know for calculating elastic potential energy and see how many joules that comes out to when it's at point A. As long as we know this distance D and the value of K, we should be able to figure that out. And then we want to calculate how much total energy at B. Well, as long as we know what this value of height is, we can get the potential energy, and if we know the speed, we can get the kinetic energy. So we'll compare these energies and see if they're indeed equal. Of course, what we're leaving out is if there's any Q value, if there's any wasted thermal energy that develops along the way. So if the mechanical energy at point A matches the mechanical energy at point B, then we can say the Q value is 0. There could be less mechanical energy at point B than there is at A if there happen to be some losses, maybe due to friction or air resistance. Okay, and then at point C, there's no kinetic energy, it's at rest. There's no energy stored in the spring, it's already released its potential energy. And so all we have at position C is gravitational potential energy, and we'll calculate that. And if the energy at C matches the energy at B, then we can say that there's no Q developed as it moves from B to C. So that's the data we have to collect, and those are the comparisons we're trying to make. Does the energy at each point A, B, and C, although it's in different forms, equate? Okay, so to start out the lab, we need to make a few different measurements. Okay, one of them is the diameter of the ball. We call that capital D. We'll use a digital caliper to do that. We'll measure the mass of the ball. That's easy. We'll just put it on an electronic scale. We're going to measure the time it takes to pass through the photogate. So what you'll see is the ball launched in real time. Here's the photogate it's going to pass through. And then when it's done, I'll hold up the smart timer to the camera and you'll be able to see what that value of time is. Okay, so those are our first 1, 2, and 3 values we need. We also need the maximum compression for the spring. In other words, how far down into the barrel is the ball when it's fully compressed. So the way we'll measure that is I'll put a piece of masking tape along the edge of this ramrod, and then we'll make a couple pencil marks, and just by measuring the distance between the pencil marks, we'll know how far we've compressed the spring. There's a preview of about how high the ball launches. Okay, which brings us to a fifth bit of data is the value of D2, how high beyond the exit point of the barrel. And actually, I'm not sure we'll get that in this segment of the video. I think I'll do that in slow motion in the next video segment. So we're going to get these first 4 data values in this part of the video. So let's start with the diameter of the ball. Easy enough. Take a digital caliper, make sure it's zeroed out, and then just put the ball in there and see what we get. Okay, there it is. Looks like it's, oops, we had it. Start over. I think it said 25.4 millimeter, which would be 2.54 centimeters, which would be basically exactly 1 inch, right? Well, 25.3 millimeter. Write that down. Okay, so there we have it. Let's get the mass of the ball. So we'll turn on our scale. The marble is going to want to roll off the pan. So we'll put this roll of tape on it, and then we'll tear the scale. Okay, so now it says 0. Put it on board, and what do we have? $66.2 grams. Okay, now we need the time it takes to pass through the photogate. That's going to help us determine how much kinetic energy it has when it's at position B, right? If we divide the diameter by the time, we'll have the speed. All right, so we put the ball in the barrel, compress it, it ratchets with 1 click, there's a little bit of energy. 2 clicks, a little more, full compression, 3 clicks in the barrel, and then I have to ready my timing device. Okay, so it's just a matter of releasing it. There we go. And what do we have? Looks like 0.0052 seconds. So So just a little more than, what is that, 5.2 thousandths of a second, 5.2 milliseconds. Okay, and then the distance that the spring was compressed. So this is where we take the tape. Place it along lengthwise going down this ramrod. Tear off that last little bit. So we're not measuring from the very bottom because it sits a little bit in the barrel to start with. So I'll make a mark right here. Here we go. So that's where the top of the ball sits when the spring is completely relaxed, and then from there we compress. Okay, make another mark. Got it. So now we just need to measure the distance between those two marks. So I'll line up the first mark at the 50 centimeter mark. And it looks like the other one is, gosh, right at, I'm going to say the other one's right at 57.0. So it looks like 7.0 centimeters is the compression D1. Yeah, from 50, oh, sorry. From 57 centimeters to 50 centimeters gives us 7.0 centimeters. Okay, so in the next video clip, we'll shoot it again in slow motion and see if we can measure the height that it rises to beyond the top of the barrel. Okay, so now we have almost all the data that we need. We've got the mass of the ball, we have the diameter of the ball, we have the time it takes to pass through the photo gate, we know how far into the barrel it is compressed by making the two marks. And then in slow motion, we have the screenshots that show us how high it rose. So it rose about, I don't know, somewhere around 145, 146 centimeters. But it didn't start at the 0 mark of this meter stick. So we have the ruler that went across, and the exit point of the barrel was at about 27.8 centimeters. So the difference between 145.8 centimeters and 27.8 centimeters is 118 centimeters. So one more time to review, make sure you've written down all the data. Diameter of the ball is 25.3 millimeters. The mass of the ball is 66.2 grams. The time to pass through the photo gates was 5.2 milliseconds. The distance the spring was compressed is 7 centimeters. And then the height beyond the exit point of the barrel is 118 centimeters. You know what we're missing is the spring stiffness. We don't know the K value. So that's the last part of this lab. So what we have is the exact same launchers set up right here. And you note that there's like a ruler that's built into the side of this PVC. And right now it's completely unloaded. So I'll read off some measurements, but this is sitting, at about maybe 6.1 or 6.2 centimeter mark. And what I'm gonna do is take some weights and start to stack them on here. And we're gonna see how much does it compress under the load of 1/2 kilogram, and then 1 kilogram, and 1.5 kilograms, and so on. Well, if we know how far it compresses, given the amount of weight that's placed on it, we can graph that all out, and from the slope of a graph of force versus compression, we can find the K value of our spring. So with no weight on it at all, it sits right at the 6.1 centimeter mark. Then we're going to take a 1/2 kilogram object, and a 1/2 kilogram weighs, right, is pulled by the Earth's gravitational field with a force of 4.9 newtons. So there it is. 0 newtons matches up with 6.1 centimeters. 4.9 newtons matches up with 6.9 centimeters. Now let's go to 9.8 newtons. A 1 kilogram object feels a force of 9.8 newtons. Okay, so with 9.8, then it sits at the 7.6 centimeter mark. And now we'll go 1.5 kilograms, so that's 14.7 newtons. And now that sits at the 8.6 centimeter mark. 2 kilograms, that's 19.6 newtons. With a force of 19.6 newtons. It sits at the 9.1 centimeter mark. And then our last data point, 2.5 kilograms. So 24.5 newtons. And it's at the 9.9 centimeter mark. So you're going to put force values on the y-axis, position values on the x-axis, and that graph will not include the origin. And that's simply because our 0 mark is kind of arbitrary on here, right? When it's unloaded, it doesn't sit at 0, it sits at 6.1. So your graph will have a y-intercept, that's fine. Regardless of the y-intercept, it's the slope of your line of best fit we're looking for. Force in newtons goes on the y-axis. Position in centimeters goes on the x-axis. The slope of that graph is going to be in newtons per centimeter. And then you'll convert that into a value of newtons per meter, so you'll have the K value in proper metric units.